Okay, so, we have been looking at description logics, and as we observed in the last class that the simple language that we were looking at was not like expressive enough to say many things, even though it did give us the advantage of using structure matching. So, now let us look at some languages which which are more expressive, and but which require more involved proof methods essentially. So, the language that we want to look at is called ALC, and the slides in this class and the next class have been prepared by Sangeeta, who is a research student in our lab and working with Professor Srinivas Kumar. So, she is an expert in description logic. So, all questions can also be answered since she is here present in the class essentially. Okay. So, we will describe the language, then we will look at the Tableau methods. I hope you remember the Tableau method for propositional logic, it is very similar in nature. And then we look at a couple of examples, and then we will look at more expressive languages than ALC. So, even in this family of languages that we are talking about, ALC is one of the simplest of these languages. Okay. So, this is a language, as you can see, there are 5 concept forming operators, as you can see here. A new thing here is this negation, where you can talk about the complement of a set. We could not do that earlier. This exists, and for all are similar to what we have seen, but we will see the details in a moment. This symbol is for and it is similar to what we studied in and in our language, our old language, but this is like or. So, it is the intersection and the union symbols essentially. So, we can talk about intersections of sets, we can talk of unions of sets, we can talk about certain kinds of role fillers, and we can talk about complements of sets essentially. The logical connectives are still the same, subsumption and equivalent. We can say that one concept subsumes another concept, and we can say that one concept is equivalent to another concept essentially. So, concepts will be represented by symbols C, D and A uppercase, roles will be represented by symbols R and S, and individuals will be represented by lowercase letters essentially. So, this ALC stands for attributive language with complement, because we are allowing the negation sign here essentially. We will see examples of all of these things here essentially. So, this is the language itself, it is a, as you can see, not a very complicated language, it is a simple language. The concepts that we can talk about are either atomic in nature, or we have this top, which is the universal concept, which we had also at some point called as thing. The bottom we had also called as nothing essentially. The negation we have already seen that if C is a concept, not of C is also a concept. The next one, which is existential quantification, is a little bit more general than was there in our language. In fact, this is what we were trying to say with the restrict R kind of a thing, or when the kind of relation we can use to define an aunt essentially. So, we are saying there exists a role filler which belongs to a class C essentially, or we can say value restriction, which means that all role fillers must belong to class C. So, this of course, is equivalent to our old statement all R D essentially, or all R C as the case may be. Oops. So, in this notation I would say all R C, where R is a role and C is a concept essentially, and this is equivalent to our and, where we say that it is an intersection of those two sets essentially, and union we did not have. So, this is something new. So, what is new here? We have this is new and this is new. and this is new. In our language. So, let us look at this language and let us look at how we can reason in this language. So, whenever we define the syntax, we have to talk about semantics, and like with the logic language and the like with the description logic that we have been talking about, semantics is defined in terms of an interpretation, a domain and an interpretation. In other words, we have a model for the language. So, the domain we will call delta, and under the interpretation I, and the interpretation function is I. And like in the language that we just saw, concepts are subsets of the domain, atomic relations are subsets of cross product of the domain, and individuals they belong to the domain essentially. So, that is the same as what we did earlier essentially. Okay. So, these are the different concepts that we have. We have the universal concept which corresponds to thing or top and corresponds to the whole set. We have the bottom concept which corresponds to nothing or corresponds to the empty set essentially. We can talk about negation. So, if C is a concept, then negation of C is a concept. What is negation of C? It is basically the complement of C. So, from the original universe we remove C and what you get is negation of C. So, for example, not human would be a concept. Existential restriction says that there exists at least one role filler which belongs to this class C. So, an example as you can see on the right hand side says that there exists has child which is who is a female essentially. Value restriction says that all role fillers must be of class C. So, for example, all children are female essentially. Now, here is something that you must always keep in mind, which we have talked about when we were talking about first order logic also, that there is a difference between such existential statements and universal statements. Existential statements assert at least the existence of one individual of that kind, whereas a universal statement says if there is a role filler then it must belong to a class. See, so which means that if for example, somebody has no children, then they would still fall in the class of being saying that all whose children are daughters essentially, even if you do not have a child. And then conjunction and disjunction are basically union and intersection this thing. So, you can say human and female, sorry, human and male, or you can say male or female essentially. So, here is a small knowledge base. You can see that there are 5 individuals Pam, Sam, Jen, Beth and Ben, and Pam has a child Sam as you can see, and that is really shown in this graphically as an edge going from Pam to Sam with a node child. Likewise, Beth has a child Ben which is shown on the right hand side. We also have information that 4 of these individuals are female and one of them is a male. And then we have these classes that somebody who has a female child, and it turns out that Pam has a female child because Sam is female. So, this set or this class which is defined by this existential quantifiers has one member in it. The set of people who have whose all children are female includes Pam. So, you can see that Pam falls in both these sets, but these 3 individuals who do not have any children, in fact they also fall in the set of people all whose children are female essentially. So, the other arrows here that you can see, these are the sibling relationship essentially which has been given there. Now, we can create new concepts from old concepts like in any description language. In fact, that is the essence of a description language. So, you can define the concept of woman for example, by saying that somebody who is not a man essentially. Maybe you might want to say somebody who is not a man and who is a human being or something like that, but anyway you can define a person as being either a man or a woman essentially. So, concepts can be either atomic, which means they do not have any definition. They can be named, which means that they are defined by some description on the right hand side, or they can be the base which occurs on the right hand side to define named concepts, or they can be complex concepts which are which use the complex this concept forming operators essentially. So, this language ALC is proportionally close in the sense that everything that you can do in Boolean logic in terms of complement, union, intersection and those things can be done in this language essentially. So, here are some examples of some more concepts. So, that is the same knowledge base that we had seen expressed graphically here. We have this notion of an aunt which we were struggling to define using our old language, but here we can say that an aunt is a woman and an aunt is somebody who has a sibling who is a parent. So, that is a thing that we tried hard in the previous class, but we found that while we could define new operators to express something like this, they were not amenable to using structure matching essentially, and in any case now we are not going to talk about structure matching, we are going to talk about different forms this thing. So, who all are aunts here? So, as you can see Pam and Jen and Beth, they all are aunts, because Pam is an aunt because she is related to Beth who has a child, Jen both the sisters have children, and Beth has Pam who has a child essentially. Then you can see that Pam and Beth are parents. So, we can define parent as has child and the class is left as the top class. So, we are not defining as to what is this thing. So, this is equivalent to our old exists. In fact, in our old exists we also had a number, we could say at least so many children. Here we are saying this is equivalent to exists one child essentially. In our old language has child. So, we can say that here as well. So, there are two parents here and there are of the three aunts that were there is one who is childless aunt. We can define a childless aunt by saying that you must be an aunt and you have no children essentially. So, again that all her children come from the empty set essentially in some sense, which means that she does not have any children, and the only one who qualifies is Jen here who does not have any child essentially. So, we have defined three concepts: aunt, parent and childless aunt essentially. Now, as I said, the interest in description logics has come because of the rise of the internet, the rise of the semantic web and the languages like OWL. Now, while OWL is a language which allows us to express such things and which is very, as you can see from this RDF like notation, it is very well defined and can be read by machines quite easily. This is not very easily read by us. So, there is also an abstract syntax for OWL, but we will not go into that here. But you can see that this relation, this which says that man, woman is somebody who is not a man, can be defined in OWL like this, that OWL is talking about a class whose ID is woman. And some of these things which we had very briefly touched upon. So, let me just mention here. So, these are namespaces. So, this concept subclass of, for example, is defined in the RDFS namespace. So, RDFS is our RDF schema essentially, and the whole idea about using something like OWL is that it is totally unambiguous essentially. You have no ambiguity about what does a word mean, because it comes from a namespace where it is defined exactly, and there is no question of sort of ambiguity in terms of when John can refer to two different people, because now we associate with everything a URI essentially, which is all hidden here, but in any case. So, here we are saying that woman is complement of, this is again an OWL term because it comes from the OWL namespace of a resource which we call as man essentially in the RDF namespace essentially. So, we have defined an OWL class here using this definition. Here is this other relation, notion of an aunt. So, we are defining a class called aunt, which is the intersection of, which is that symbol in our description logic, these two classes, one is woman and the other thing is this whole restriction on property has sibling, and the restriction is that you must be a parent essentially. So, the kind of restriction R that we were trying to define earlier is in fact used in OWL language here. So, this is I have shown you these two OWL statements only to motivate you by for looking at description logics, because they are useful in modern day, for example, e-commerce or whatever you want to do, anything to do with the semantic web, social network analysis if you want to do. Now, a knowledge base consists of two kinds of things. One is called the TBox or the terminological box, and the other is called the ABox or the assertion box essentially. So, the TBox basically contains axioms on concepts, how are concepts defined in terms of other concepts and all those kind of statements, and ABox is talking about individuals essentially. Okay. So, the notation used in OWL is that it is a very straightforward notation. So, for example, we can say, as you can see here, that Pam has a child called Sam. We can simply express it like a predicate in first order logic, that has child is a predicate, Pam is the resource in these terms, and Sam is the role filler essentially, or we can say that Pam is a female essentially. So, this is part of the language ABox. Our knowledge base consists of statements of the kind that we saw, plus these ABox assertions essentially. Now, the Tableau, which is a proof system. So, if you recall, a Tableau method is basically a method to try and construct a model of a set of statements or a set or a given knowledge base essentially. So, in the case of propositional logic, if you remember, we said that okay, if P is true and Q is true and R is false, then my whole sentence is satisfied essentially. And then actually what we had done is that instead of trying to show that something is satisfiable, we had said that or something is true, we had taken its negation and we had tried to show that the negation is unsatisfiable, and all the paths were closed in the sense that you could not construct any model for the set of statements. This is precisely what we are doing when we reason with description logic. In fact, description logic is a subset of first order logic. Everything that we are writing in this language, for example, ALC, we could have written in first order logic as well essentially. So, a Tableau is a directed graph which is aimed at creating a model of a set of statements essentially, and the nodes in the graph are associated with individuals and they have associated with them labels essentially. So, we have for every individual we have a label called L of x, which contains all the concepts that this individual belongs to essentially. Okay. And then there are relations between nodes which are edges in the graph which are labeled by these two individuals essentially. Okay. So, what are the reasoning tasks that we are interested in? One of them is the knowledge base satisfiable? Then we have this inference task. So, that is satisfiability, that can a statement be inferred from a knowledge base, and remember that one of the key statements we were interested in is a concept C subsumed by a concept D, or is an individual D belong to a class D. So, we will see how all these are done, and in the case of Tableau systems for description logic, we convert everything into showing that something is unsatisfiable. So, just like we did for the resolution method, that we take the conclusion, take its negation and add it to the knowledge base and then show that it is unsatisfiable by deriving the null clause. Here we will show that all options that the Tableau has, or all branches of the Tableau will end up being closed, in a sense that they will always contain something and its negation essentially. Okay. So, some little bit of detail we need here. So, to work with the Tableau method, we need to work in something called negation normal form. So, remember that when we were talking about the resolution method, we said that everything has to be in the clause form or conjunctive normal form. In the case of Tableau methods, it has to be in this negation normal form. We will see shortly how to do that, but some of the key steps are that you convert a statement like A is subsumed by B to not A or B essentially. So, if you remember A subsumed by B is something like saying A implies B. So, for all x A x implies B x essentially, which is equivalent to saying that either it is not A x or it is B x essentially. So, we can do that equivalently, and likewise equivalent can be replaced by these two sentences essentially. So, in the negative normal form a negation occurs only before an atomic concept, exactly like in the clause form negation has to be pushed inside, even here the negation has to be pushed inside. So, if you had a statement like not the concept or the complement of somebody who has a child who is a person, by pushing the negation inside the same kind of rules apply. So, De Morgan's will convert this existential into universal, and then that negation will get pushed inside into this not here essentially. So, essentially we convert the knowledge base plus the negation of the conclusion into negative normal form, and then we use these so called expansion rules by adding new descriptions or by breaking down the descriptions, in other words, till either we get a closed branch where you have a concept C and its negation, in which case the knowledge base is unsatisfiable. But if there is some branch which is not closed, then actually we have a model for the system, and then we can say that the knowledge base is satisfiable essentially. So, conversion to negative normal form, these are the things. So, on the left hand side you can see a concept inside the brackets, and on the right hand side it is negative normal form essentially. So, negation NF of C is just C itself, and NF of not C is not C if C is atomic, then not C you just remove the not. Negation of top is bottom, negation of bottom is top. The negative normal form of C intersection D is the negative normal form of C intersection within. So, very similar to the process by which you convert things into CNF essentially. You can see that something like De Morgan's law is applied here, when negation of C intersection D gives you negation of C union negation of D essentially. So, that is like De Morgan's, and these other things are this thing. Likewise, as you can see that this is another variation of De Morgan's law. In fact, with the quantifier, that negation of a universally quantified statement is an existentially quantified statement, and the negation has gone inside essentially. Likewise, for existentially quantified statements. Now, these are the expansion rules, which means if you have labels for an object and the labels are not simple, how can you break them down into simple labels essentially. So, these are the different rules. So, the AND rule says that if C intersection D belongs to the label of x and C and D are not already present in this label of x, then this notation says that you add C and D individually to the labels of x essentially. So, that is the AND rule. The OR rule says that if you have C union D in the label of x, then you have actually a choice point essentially, because it can either belong to C or it can belong to D or it can belong to both, of course. So, you either add C to the label of x or you add D to the label of x. So, you can see that this will create a branch like this, where either the left hand side could be a model or the right hand side could be a model, but if both are not models or if both are closed in some sense, then we can say that the original thing is unsatisfiable. Then there is a existential rule. So, we have a label of x which contains this statement that it has a role filler which comes from the class C, and there is no edge going to some new symbol y. So, we create a new node y. So, we create x, then we create y, and then we add to the label of y this class C essentially. We will see examples as we go along essentially. The all values from in terms of owl. So, owl would say some values from or all values from. So, this the universal rule is all values from. the important thing is this if there exists an edge from x to y, then for y label the class with C. So, for that y label the class. For every edge that is going out of x with the label this one x y, label the other endpoint with the class C essentially. And then there is a TBox rule which says that if there is any TBox statement, you can apply it to any individual in the knowledge base that you are talking about. So, if there is any statement S, then you can add it to for any label in the whole thing. So, we are going to be talking about satisfiability. So, here are two very small knowledge bases. One says that women are not men, and then we say that Alex is a woman and then we say Alex is a man. So, obviously, this should be unsatisfiable essentially. So, and I will leave this as a small exercise for you to construct a tableau for this to show that it is unsatisfiable. The second knowledge base says that women are not men and Alex is a woman. This is clearly satisfiable because you can see that there is nothing which is contradictory in these two statements essentially. So, why do people want to check satisfiability of knowledge bases is because if the knowledge base becomes unsatisfiable, then it kind of reflects on some kind of modeling error essentially. When we are looking at logic, we had seen that if a set of statements is unsatisfiable, then you can actually prove anything from that essentially. So, basically it is not a desirable thing to have essentially. So, what is the algorithm for now checking for unsatisfiability? So, let us say that there is a knowledge base K and a statement S, and we want to ask the question that does K entail S, and like we did in the case of resolution method, we will end up showing that that K union negation of S is unsatisfiable. So, that is a basic high level algorithm. So, how do we do? We first start off by negating S, then add it to the knowledge base K, then we do all these conversions that we had spoken about, replace this symbol with a statement like this, replace the equivalent symbol with two of these and in turn by the union and the negation symbol. After that, you convert it into negation normal form, which basically means you push the not inside, and then use the statements on individuals who are there in the knowledge base to create an initial graph, and then you use expansion rules one by one to expand that graph and try to show that it is unsatisfiable. Remember that at this stage we have constructed a knowledge base which is K union not of S. So, we expect, so if K entails S, we expect K union not of S to be unsatisfiable, which means that all expansion rules when we try, all the branches, all the options that are accessible to us must be closed essentially, very similar to what we did for the Tableau method in the this thing. So, a contradiction occurs at all if all choices, if a contradiction occurs at all choices, then our original statement that K entails S is true, but if there are some branches which are open, which means they are satisfiable, then what is satisfiable? K union not of S. So, when K union not of S is satisfiable, it means that K does not entail S, because you can have K and you can have not of S at the same time essentially. So, this is a high level algorithm. I will stop here, and in the next class we will look at a detailed example, and then we will also look at a couple of languages which are more expressive than ALC, and what is the kind of languages which are popular now, what are the different new kinds of things we can say essentially. Notice that in ALC that number is missing essentially. In our old language you could say there exists at least n role fillers. Here you cannot say that, you can say there exists a role fillers from class C, or all role fillers must be from class C, but you cannot put a number to that essentially. You cannot say there are at least 2 role fillers to class C, but we will see that there are languages which do that, and as and when you keep adding more expressivity, the complexity of the theorem proving process becomes harder and harder essentially. So, we will stop here and we will take this up in the next class.